Then here the requested is to evaluate the limit when n goes to infinity, ln divided by. As it's done, we did this kind of limit in once we talked about function and what we can do once it's a function. Once it's a function, once the requested was the limit of ln x divided by x. Obviously, when x goes to infinity, this limit, in order to do it, what we did, we talked about Hospital's rule. That means we evaluate the derivative for the denominator and for the numerator. Then we evaluate the derivative of, in order to evaluate this limit, we have just to evaluate the derivative of ln x, which is 1 over x, and the derivative of x, which is 1. And obviously here the limit is equal 0. That's why this limit equals 0. And once this limit equals 0, then the limit of ln divided by n when n goes to infinity is also equal 0, thanks to the theorem studied a few minutes before. That means this theorem, when he said, not this one, exactly this one, if this limit, if limit when x goes to infinity of f of x equals capital L, then also an goes to L when n goes to infinity. Thanks to theorem 3 or this theorem, anyway, in slide 13, we can conclude easily this limit is equal to 0. Then, in one word, we have just to, if it's possible to evaluate to look at this expression as function and to evaluate the limit in infinity, then we have the same limit. Why? Because once it's a function, we can apply Hospital's rule and so on. For example, 7, here an is equal minus 1 to the n. Is it convergent or divergent? The answer is divergent, because this function, this sequence, the sequence is equal minus 1, then 1, then minus 1, then 1, then minus 1, then 1, then no limit. That means we don't have any limit. The sequence does not approach for any real number. And sometimes it's equal 1, and sometimes it's equal minus 1. That's why it's the sequence is divergent. However, once we divide by n, even the sign is not fixed, however, the sequence goes to 0. Why? Because in terms of absolute value, it's small enough. It's equal 1 over n, and 1 over n goes to 0. And we talked before about this when we said if the limit of the absolute value of any sequence is 0, then the sequence goes to 0 without absolute value. Here we have the same situation. That means the limit with absolute value is 0. That's why without absolute value, by theorem 6, this limit is equal to also 0. We can be careful. Even for function, we have this situation. Once the limit of the absolute value of the function is 0, then the function is 0. However, be careful. Once it's equal 1, this formula is wrong. That means be careful when I said limit of an, be careful, it's wrong. When limit of absolute value of an, the absolute value is equal 1, then we cannot see anything, because here, like that, the sequence verifies the following limit. That means the limit of absolute value is equal 1, because once we take the absolute value, we remove minus, and we remove minus for the sequence, and it becomes 1. However, without absolute value, be careful. Sometimes it's 1, sometimes it's negative 1. That's why this is a divergent sequence. But then be careful. Once it's without small multiplication by a small sequence, it's no, it's divergent, but here it's 0 because it's -1 to the n times something small, which is equal, then the limit equals 0. Another thing related to sequence is this sequence is a basic sequence which is r to the n. For example, 2 to the n, or 5 to the n, or 1 over 3 to the n. We have a lot of sequence like that. What about the limit 1 over 3 to the n? What about the limit of the first sequence, 2 to the n? 2 to the n, Shabab, the sequence goes to what? 2 to the n. We have 2, then 4, then 8, then 16, then 32, and so on. As you see here, this limit is equal infinity because the sequence becomes large and large enough. That means here we have 2 to the x, 2 to the n goes, or any a to the x goes to infinity if a is more than 1, and a to the x go to 0 when a is between 0 and 1. Therefore, we have this formula that means r to the n goes to infinity when n goes to infinity if r is more than 1, and goes to 0 if r is between 0 and 1. Then this is two different situations. Then we have to check if r is more than 1 or if r is between 0 and 1. طبعا if r is between -1 and 0, then its absolute value of r is between 0 and 1. That's why the limit of absolute value of r to the n is equal 0. Then even if r is between -1 and 0, the sequence goes to 0. However, when r is less than -1, then Rn diverges. Then to summarize, we have three situations. Then we have when we talk about r to the n. من الأول تحدث when r is positive, but when r is any real number, this limit, we have three situations. If r is more than 1, if r is more than 1, this is infinite. If r is more than 1, this is infinite. If r is between -1 and 1, between -1 and 1, in this case, this limit is 0. If r is less than -1, less than or equals, here this is the only case when we talk about equals, then the sequence is divergent. Less than or equals -1, the sequence is divergent. Then this is the Phillips situation for any real number. If r is more than 1, it's infinity. If r is between -1 and 1, it's 0. If r is less than -1, it's divergent. Obviously, if r equals 1, it's a constant. And if r equals 1, the remaining part just when r equals 1. When r equals 1, it's a constant. It's the sequence 1. That's why this limit is equal 1. Here, this is in the figure 11, we have That is one figure shows the graph of the variance R. This is when R equals -1. When R equals -1, and sometimes it's 1, and sometimes it's -1, then it's divergent. When R is more than 1, then the sequence becomes large enough and it goes to infinity. And when R is less than -1, and sometimes it's large enough, and sometimes it's negative enough. That's why no limit. The limit does not exist, and we call it, this is a divergent sequence. Then this is all. طبعا هنا لخصنا. When R is between -1 and 1, then this limit is equal 0. The limit is convergent. If when we talk about R to the n, it's convergent if it's equal 0 if R is between -1, 1, and it's equal 1 if R equals 1, obviously, because it becomes a constant sequence. And if R is outside, it's divergent. That means sometimes it's infinity, and sometimes it's this limit does not exist. However, it's divergent. This is all about convergent and divergent. Now we move to monotony. That means at what time you have an increasing sequence, and at what time you have a decreasing sequence. The definition is very easy. We have an increasing sequence when an plus 1 is more than an for any times, for any n more than 1. بمعنى دائما sequence is increasing. بمعنى A2 is more than A1, A3 is more than A2, and so on. Okay. Then for any AN is more than AN plus 1 is more than AN. If we have the inverse situation, then the sequence is decreasing. Be careful. Then we talk about increasing or decreasing. If we have AN is more than AN plus 1, or if AN is less than AN plus 1. As example, what about the sequence is decreasing or increasing? The answer is decreasing. What should I do? I have to evaluate, to compare AN and AN plus 1. انتبهوا لما يكون عندي نفس البسط بس المقام يصبح أكبر، إذا دائما لما المقام أكبر الفراكشن يصبح أصغر. Okay, that's why here, لأنه here what is the difference between this term and this term? Here we have n plus 1 instead of n. That's why the denominator becomes more. Here on the right side the denominator is more than n plus 5. That's why in terms of fraction, this is less than this one. That's why we have AN is more than AN plus 1. That means the sequence is decreasing. When AN is more than AN plus 1, that means we have a decreasing sequence. بمعنى كل ما نكبر في الN كل ما تنزل السيكونس, then we have a decreasing sequence. Okay, this is then the target is to compare AN plus 1 and AN in order to have idea about about the monotony of the sequence. That means if the sequence is increasing or decreasing. This is another case when the requested is to compare, to check if why this sequence is decreasing. The idea is very easy. We have to compare, or maybe we have, I can do better. I can evaluate AN plus 1 minus AN. And I verify if this expression is negative or not. Then I have to evaluate. I have to prove AN plus 1 minus AN. AN plus 1, I'm sorry, minus AN. Okay. Then I have to evaluate AN plus minus 1 minus AN. Or here what he said, here he said that we must show that AN plus 1 is less than AN. Then this is AN plus 1. That means we substitute, we put N plus 1 instead of N. Here we put N At what time we have this inequality? We have this inequality when we multiply here by n squared plus 1, and here, that means here we have a divided by b is less than c divided by d if the cross multiplication is the left n plus 1 times n squared plus 1 is less than n times n squared plus 1 plus 1. Here he tried to remove parentheses, okay, and we obtain n squared plus n is more than 1, which is true. Okay, طبعا أنا أقول it was better to do what I said. That means we evaluate an plus 1 minus an. Once we evaluate an plus 1 minus an, we obtain easily it's negative. That's why the sequence is decreasing. Okay, بمعنى نحسب an plus 1 minus an. Once we do this, we reduce in the same denominator. We have an plus 1. We have some computation. An plus 1 minus an. We obtain, after some computation, we obtain 1 minus n squared minus n. Divided. طبعا لما نوحد المقامات ونسوي simplification, we obtain this one, this equality, 1 minus n squared minus n divided by n squared plus 1 times, قلنا نوحد المقامات n squared plus 1 times n plus 1 squared n plus 1 squared plus 1 طبعا, which is negative. Why? Because we know 1 minus n squared minus 1 is negative. لأنه n تربيع هي أكبر من n تربيع أكبر من 1 و n أكبر من 1. Then n squared is more than 1, n is more than 1, then n squared plus 1 is more than 2. 1 minus something more than 2 is negative. That's why the sequence is decreasing. Then we have to evaluate an plus 1 minus an, or to use this way, it's this. طبعا here it's another way. Here we try to use the function. It's another solution too. We consider this function and we evaluate its derivative. Once we evaluate its derivative, x is more than 1, obviously, because we are interested of f of 1, f of 2, f of 3, and so on. Because f is decreasing because its derivative is negative, then we have a decreasing function. What is the meaning of decreasing? بمعنى كل ما تكبر الx كل ما الاوتبوت يصغر. بمعنى we have f of n plus 1 is less than f of n. This is the meaning of decreasing function. As we look at this solution here, we use the monotony of the sequence of the function thanks to the derivative in order to cope. This is another way to do the same thing. Once it's easy to evaluate the derivative of the function, and we can use this way to conclude. Okay. هذا تقريبا ما عندنا بالنسبة للsequences. Then another thing, we call it the sequences is bounded above or is bounded below if we have this kind of inequality. An is less than something, or an is more than or equal something independent of it's a constant. Capital M and small m are two real numbers. Okay. Then if we have this kind of inequality, we call it this sequence is bounded below or above. Then here, if we have both, if it's above and below, then it's bounded. It's a bounded sequence. For example, when we take n divided n plus 1, it's a bounded sequence because it's positive and it's less than 1. That's why it's bounded. However, an equals n is not bounded. It's positive, but it's not bounded below because it's not bounded above because n goes to infinity. Then no way to obtain any real number such that n is less than this real number. لأنه هنا السيكونس تصبح كبيرة مرة when n is large enough. However, it's positive. Okay, when we look in the left side, it's positive. And for this sequence, it's bounded because it's more than, it's between 0 and 1. The sequence also is bounded because it's between 1 and minus 1. However, okay, the sequence is bounded, but it's not, we don't have any monotony. That means when we evaluate, in sometimes it's 1, in sometimes it's negative 1, then it's not a decreasing function, and it's not also an increasing function. Then be careful, no relation between bounded and decreasing or increasing. We have to look at each information لحالها. Okay. No relation. We have two independent information. That means no relation between a bounded or bounded below or above, or decreasing or increasing. However, once we have an increasing function, verify an is less than capital M, then this sequence, an increasing sequence, then the sequence goes to converge. That means we have a limit which is less than capital M, less than or equal. This limit can be capital M. But anyway, once the formula is, the theorem is the following: when we have an increasing function and an is less than capital M, then in this case we have a convergent sequence. That means if, no need to talk about the proof, but the main important point, once you have a bounded sequence, if we have a monotony, if it's decreasing or increasing, then it's convergent. Then when we have in same times bounded in the decreasing or increasing, then the sequence is convergent. Then be careful. We have two independent information. The first one is bounded. That means we have two constants that an is between capital M and small m. And the monotony, when we talked about, it's an plus 1 minus an is positive for any n, or it's negative for any n. Once we have monotony, that means once we have decreasing or increasing, and we have bounded in these times, we are sure once we have in same times bounded and the monotonic sequence, then we have a convergent sequence. This is all for this section.